All right, so today we're going to finish up ionic nomenclature. There's only one little detail we have to talk about there. Then we're going to get into covalent nomenclature, and we're going to do single and double displacement reactions. So a lot of ground to cover in this remaining portion of the class. All right, let's talk about hydrates. Hydrates have water as part of the formula. We're going to be doing an experiment in a few weeks involving hydrate. Excuse me. So, for instance, this substance is deliquescent. That's your word of the day. It means very hygroscopic. Oh, what does that mean? Hygroscopic means it absorbs water from the atmosphere. So these are things, you know those little packets, like when you buy a new purse or pair of shoes, got a little packet inside to absorb moisture. It's not usually zinc chloride in there, but that's the kind of substance that's in there. It absorbs moisture. Okay? And so zinc chloride is actually so deliquescent, we call it hygroscopic, which means if you leave it sitting out, it'll form a solution of itself from just absorbing water from the atmosphere. So there are 4 hydrates here. 1 is the prefix here, 2, 3, and 4, right? So zinc 2-chloride hydrate, dihydrate, trihydrate, tetrahydrate, right? So all you're doing is you're looking at this and then putting the appropriate prefix and then the word hydrate, okay? And this little dot is just like a time sign, like when you're multiplying. Okay, so don't think of it like that. If you want to write it as an X instead of as a dot, makes no difference to me, all right? But that's what a hydrate is. Now, you need to memorize your prefixes. So if you don't know your prefixes from other classes, it's time to learn them, okay? The mono prefix is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa 8, nona 9, and deca 10. I won't make you go beyond 10, okay? 10 fingers, you can learn your prefixes, just count them off. All right, you're gonna have to know prefixes for both hydrate nomenclature and for covalent nomenclature. You can't name covalent substances without knowing the prefix system. Okay, so you're gonna have to learn them for both. So the good news is it's the same prefixes. And then we use the word anhydrous anytime the water has been removed. So in the experiment we're gonna be dealing with, you're gonna deal with both the anhydrous version and the hydrated version. Okay, of the hydrate that we're dealing with. So anhydrous just means that the water has been removed and you're left with salt without the water. Make sense? Ready to try some? Okay, name these and then write formulas for these. All right, let's go over the answers for these hydrates. So you have to know your prefixes in order to do this. Naming this part's just naming the compound, right? That's no different. You just name the compound, and then you just figure out what the prefix stands for the correct number, and then plop the word hydrate at the end. Yes? So, copper 2 sulfate pentahydrate. Penta means 5. Do we agree? Why is it not magnesium 2 sulfate? Does magnesium need Roman numerals? No. Manganese does. Magnesium does not. Right, so it's just magnesium sulfate heptahydrate. Lead 2 acetate trihydrate. Just want to take a minute here to point something out to you guys. There are 2 acceptable ways to write acetate. Your book uses acetate as CH3CO2-, but that's also the same thing as C2H3O2-. Okay, so you can use either one. Some students prefer to write acetate like this because it's got all the C's together, all the H's together, and all the O's together. So it's kind of more combined, but they're both acceptable. Okay, this is more what the Lewis structure looks like. This is just combining all the like terms. Why do we need the 2 after lead? Lead's not in the transition metals on the periodic table. It's one of the exceptions, right? All right, going the other way around, sodium carbonate, Na2CO3, deca means 10, excuse me. So there we have it. Copper 2 sulfite, that would be CuSO3, penta means 5, and then hydrate first H2O. If you made a mistake, you see where you made it. We good on these. All right, now let's get into covalent bonding. So covalent bonding is an entirely different animal than ionic bonding is, right? In ionic bonding, one atom loses an electron and becomes a cation, and the other one gains an electron and becomes an anion, right? So we've got a positive and a negative. There's an extremely strong electrostatic force of attraction right there, right? So you can think of it as the cation donating the electron almost, right? It's very, 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 very strong bond between that cation and that anion. We call that an ionic bond. When we're talking about covalent bonding, okay, that's totally different. In this scenario, electrons are being shared, right? So in ionic bonding, we gain or lose electrons to become electronically stable, and that's what gives us our cations and our anions. Whereas in covalent bonding, we share electrons between atoms, and that's what gives them electronic stability. Okay? If you want to talk about naming, right, these two words get thrown around. Sometimes you hear molecule, sometimes you hear the word compound. What's the difference between them? Well, traditionally, we talk about a compound as a substance containing ionic bonding and a molecule as a substance containing covalent bonding. Okay, that's the only real difference there. Will I make fun of you if you accidentally use one in place of the other when you're writing a lab report? Probably not, right? But just so you know, I like to inform you for your general knowledge, right? What's the difference between a compound and a molecule? It generally refers to the type of bonding. All right, now again, electrons are shared. So here's an example using H2, okay? In this example, this pair of electrons is shared between these two atoms. And down the road a little bit, we'll talk about what degree that pair is shared. Is it shared evenly? Is it shared unevenly? Here it's being shared perfectly evenly. But we will get into examples later on where it's not. What does that do to things? Okay, so you can look at a formula and tell immediately the bonding type just by looking at the formula, okay? If it's ionic, it'll be one metal and one nonmetal, right? Metals form cations, nonmetals form anions, so metal plus nonmetal. Or it could be a metal and a polyatomic ion, or it could even be two polyatomic ions, right? Ammonium nitrate, for instance, that's two polyatomic ions. So that should be a dead giveaway. You've got ionic bonding. Whereas in covalent bonding, it's always two nonmetals, okay? And just FYI, when you're looking at the periodic table for this in particular, we're pretending that hydrogen is sitting next to helium in the nonmetals group, okay? So if you see something involving hydrogen, for instance, we're pretending that hydrogen's sitting in the nonmetals. So just keep that in mind, all right? But this is one of the things that will be on your proficiency, okay? It'll say name, type of bonding, and then formula. Okay, so if I give you the formula, you'd figure out what its name is, and then from the formula, you can tell if it's ionic or covalent. All right, prefixes are the same. We use the exact same prefixes that we do in the hydrates, which is why I teach these two things together. And then you use the prefix system to tell how many of each element you have. All right, so when we're looking at, let's pretend we're doing this example. Na3P. What's the name of that? You just took a quiz, right? Sodium phosphide, right? Okay, that comes from Na plus and P3 minus, right? Does that 3 factor into the name at all? No, it doesn't, okay? In covalent naming, those subscripts do factor in, okay? They do factor in. The subscripts are part of the name. That's another dead giveaway between ionic and covalent bonding, because you're not going to see tri and penta and tetra and octa in ionic nomenclature, but you will see it in covalent nomenclature, because that's a big, big difference. So let's go through these together. Boron and bromine, are those both nonmetals? Confirm this on your periodic table. Yes, they're both nonmetals. So what's the prefix for 4? Tetra, good. And what's the prefix for 8? Octa. So it would be tetraboron octabromide. They don't exactly roll off the tongue easily, right? So they are kind of a mouthful. Again, you have to memorize those prefixes, okay? That's something you have to learn. There are only 10. You probably already know the majority of them, if not all of them. All right. Are both of these nonmetals? Yes, they are. So what's the prefix for 6? Hexa, and the prefix for 9? No, not right. So selenium and silicon, silicon becomes silicide. So hexaselenium nonosilicide. Okay, the second element's always going to end in "ide." Does this make sense? Covalent nomenclature is totally different from ionic nomenclature. It's a completely different animal. So make sure you understand how to do this. And again, you can tell that this is covalent nomenclature first and foremost. If I gave you this and asked what kind of bonding it is, if you see prefixes, that should automatically make you think, yep, this is definitely covalent, right? Because ionic doesn't use those prefixes. Or you can look at the periodic table, right? Selenium and silicon, both nonmetals, that's a giveaway too. And if I asked you what type of bonding it was, you can look either from the formula, right? Se, Si, or from the prefixes, right? Both of those would tell you. You're dealing with covalent nomenclature here. Now, here's something that happens for ease of pronunciation, okay? It happens when something ends, when you're naming an oxide, and the prefix ends in O or A. So let me give you an example of that. Dinitrogen pentoxide, right? We dropped the A because dinitrogen pentoxide, that doesn't flow off the tongue, and it kind of ends up getting dropped anyway, right? So it's dropped from the spelling too. So it's dinitrogen pentoxide, right? That back-to-back vowel is tough to pronounce. It usually ends up getting merged into one anyway. Does this make sense? So if we were naming water, let's just practice. H2O, right? Water has covalent bonding. Water's not ionic bonding. It's very, very much covalent bonding. So what prefix goes with 2? So that's dihydrogen. Is it monoxide? It'd just be monoxide, right? Okay, that second O gets dropped. Makes sense? That's the systematic name for water. Again, that A got dropped. Okay, here's another important detail. If there's only one of the first element, we drop the mono only if it's the first element. Okay, so for instance, NO2 is nitrogen dioxide. Think about CO2, that's carbon dioxide, right? It's not monocarbon dioxide, it's just carbon dioxide. Same thing here. It's not mononitrogen dioxide, it's just nitrogen dioxide. Now, if the second element only has one, you still keep the mon, right? Like in dihydrogen monoxide, right? You still keep the mono, drop the O if it's an oxide, right? But you still keep that prefix if the second element only has one, but not the first, right? So it's not called monocarbon monoxide, it's just called carbon monoxide, okay? Make sense? Go home tonight, make sure that you've got a carbon monoxide detector in your house. If you don't, go buy one. Save your life, literally. Saved my family's life a couple years ago. Okay, let's pretend that this is an exam question. Which is the correct answer? A, B, C, or D? C, good. Why is it C? What? You don't need the repeating the O, right? So that eliminates those two. And you don't need the mono for the first one, right? So all you're left with is C. Good. Okay, take a second and name these. Just take a quick second. Okay, what prefix goes with 5? Penta, and what prefix goes with 7? Hepta. Are these both non-metals? Yes, I mean, technically GE is a metalloid, but it's close enough. So pentagermanium, excuse me, germanium. Oh, and I said it right. Geranium is a plant, germanium is the element. Pentagermanium heptoxide, right? We dropped the A. It's not heptaoxide, it's just heptoxide. All right, are phosphorus and bromine both nonmetals? Yep. So prefix for 4 and prefix for 3. So tetraphosphorus, tribromine. Did you get them right? All right. So again, you can tell type of bonding by looking at the formula. So what kind of bonding is in water? We already talked about it. What about ammonia? Ionic or covalent? Covalent, right? Remember, we're pretending hydrogen's over next to helium. CO2 would be covalent, NaCl, ionic, N2O, covalent, CaCO3, ionic, NaHCO3, ionic, MgSO4, 7H2O. That's actually ionic. That's just a hydrate, remember? And what about this one? MgOH2. Ionic. Good. Okay, now think back to last week. Remember, we did 3 types of reactions. We did synthesis, decomposition, and combustion. And I told you this week we're going to add 2 more to the list. So here you go. Now that we can write formulas, these 2 are appropriate to talk about. We're going to do single displacement and double displacement. So here's what happens. This is always a reaction between a metal and a compound. Okay, a metal and a compound. So here C is our metal. And when you see the word metal, think periodic table. Okay, if I say aluminum metal, that's Al, right? Not aluminum ion. Students get metals and ions mixed up, right? Aluminum ion is Al3+. Aluminum metal is just straight up Al. So this is my metal, this is my compound. So the metal becomes the new cation, and the cation becomes the new metal. And then this anion just stays the same, right? So A gets all by its lonesome, and now C and B get together. Why is it CB and not BC? Who goes first, the cation or the anion? Cation goes first, right? Okay, so here would be an example of a single displacement reaction, right? AgSO4 plus Cu producing Ag plus CuSO4, okay? Now, in this case, copper's a metal, right? And it's in the transition metals. So it could be copper 1 or it could be copper 2. Now, if we're going to do this experiment in the lab, actually, we're going to do this in the lab. Excuse me. And you'll see by the color which version of copper you're dealing with. Copper 1's green, copper 2's blue. So you'll tell by color which copper you've got. If I was giving you something like this on an exam where I'm giving you a transition metal and then you're turning it into an ion, I'd either tell you the ion has a charge of whatever, or I'd accept both. Okay. Does everyone understand single displacement? Now, double displacement is when 2 compounds are reacting, okay, and everybody gets mixed together. So A, who's A going to be paired with? Is A going to be paired with C or D? Why is AC not possible? Because A and C are both cations, right? So that wouldn't be a compound. That wouldn't work, right? So A and D are going to be together. And is it going to go AD or BA? AD, right. And then that obviously leaves B and C. Is it going to go BC or CB? CB, right. Always put the cation first, okay? A and B split, C and D split, right? Now, here's a real world example of that. I want to show you this one because this is a really common mistake I see. A lot of students will say, oh, okay, there's a subscript of 2 here, so I need to just carry that subscript of 2 and put it over here. Why is that wrong? Why does there not need to be a subscript of 2 here? Why not? Because the subscripts come from the charges, right? Right, K is +1. So you don't need a subscript of 2 because K is plus, BR is minus, right? That's a 1-to-1 ratio. Okay? So this is a really common mistake I see students make. They'll say, oh, subscript of 2 over here, so there must be a subscript of 2 over here. That's not true, okay? You need to ignore any subscripts on the left when you're writing your formulas on the right, okay? Because the formulas on the right have nothing to do with what the subscripts were on the left. You just need to look at what is my cation, what is my anion, and then crisscross them, right? That's where your subscripts are coming from. And if you're dealing with a transition metal, this is copper 2 over here, so it's going to stay copper 2 over here. Transition metals aren't going to change unless we're doing a redox reaction, which we're not dealing with right now. All right, so I'm going to give you a minute to try this one. I'm going to pause the recording, so bear with me for just a second. Okay, let's go over this one. So what kind of reaction is A? Single displacement or double displacement? That's double displacement, right. Now again, this is why we've got to memorize our polyatomic ions, okay? Because we're totally stuck if we can't write formulas. And those formulas are contingent on us knowing our polyatomic ions. So here's what I got. Check your work, see if you agree. Fe2SO43 plus 6 LiOH produces 2 FeOH3 plus 3 Li2SO4. We're going to take equations like this a little bit further when we start talking about solution chemistry, but for now, this is all we need to worry about. Did you get it right? You missed it. You see where you made your mistake. Practice, 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 okay? This just takes repetition. I have a lot of practice problems on the course page. If you go to the content tab and click on the folder, it's called Practice Problems for You to Try. I've got a ton of this kind of stuff on there with the answer key, both for naming compounds and for writing reactions. All right, B, what kind of reaction is that? That's single displacement, good. Aluminum metal, is the formula for aluminum metal Al or Al3+? It's Al, okay? If you wrote Al3+, write -1 next to your answer, okay? Because Al3+ is an ion. Aluminum metal, that's what's on the periodic table, okay? So this is single displacement. 2Al plus 3 MgSCN2 produces 3 Mg plus 2 AlSCN3. Thermodynamically, probably not going to happen. I didn't calculate delta G, but I'm assuming that this is a reaction that's not going to happen. We can study that next semester in Chem 2. Formation of magnesium metal is pretty low probability under standard conditions. But as long as you understand it, we'll worry about thermodynamics later. Questions on these two? If you made a mistake, do you see where you made it? Because the purpose of doing these exercises is to try it for yourself, right? It makes more sense to watch me usually than it is for trying it for yourself. So I always want to try things for yourself as opposed to just watching me. All right, here's another one. Write the balanced equation to represent the reaction occurring when sodium chlorate and manganese 2-phosphate react. What kind of reaction is this? Give me a second here. Let me pause the recording. Over this one. So I'm going to go through it on the board so we can all make sure we're good, right, on the crisscrossing and the formulas and everything. So sodium chlorate comes from what sodium ion? Na, what charge? Plus, right? And chlorate, what's that? ClO3 minus. So when we crisscross those, that's just NaClO3, right? Manganese 2, so that's just Mn2+. And what's phosphate? What's phosphate? PO4, what charge? 3 minus, right? So when we crisscross those, that gives me Mn what? Mn3, PO4, 2. Okay. Now this is a double displacement reaction, right? So that means that sodium is going to get together with, excuse me, phosphate, right? So sodium is going to get together with phosphate. So when you crisscross those, you get Na3PO4, right? And now manganese 2 is going to get together with chlorate, right? So Mn2+ and ClO3 minus. So what is that? Crisscross those. MnClO3 2. Now, is this balanced? No, it's not balanced. It's not balanced, okay? So if you still are having problems with balancing equations, go back and work on those practice problems that are posted online. I'm just going to give you the answer. The easiest way to get good at balancing equations, again, is repetition, okay? Your coefficients, 6, 1, 2, 3. That's double displacement. All right, last one. Calcium cyanide and cobalt-2 chromate. Let me pause the recording here. All right, last one to go over. I'm going to go through this one on the board again. I think students benefit from seeing me work it out. Yes? Yes? All right, so let's go through it together. So what's the charge on calcium as an ion? Ca2+, right? And cyanide, what's that? Not CH, Cn. What charge? Minus, right? So when those get together, crisscross those, that becomes CaCN2. Is that right? No, what's wrong with that? It must include parentheses. Good. Monatomic ions, for some reason, not monatomic ions, Cn minus and OH minus, for whatever reason, students forget the parentheses there. Okay, and cobalt-2, so that's CO2+. What's chromate? What's the charge? 2 minus, right? So is it subscript 2, subscript 2? Are the subscripts both 2? Is it CO2, CrO4, 2? No, what is it? It's not 2 to 2, it's 1 to 1, right? CO, CrO4. Okay, so those are my reactants. Now, what kind of reaction is this? Single displacement or double? This is double displacement. So calcium's going to get together with chromate. Right, so I'm going to have Ca2+ and CrO4 minus. Oops. So that's just CaCrO4. And then cobalt-2 and cyanide. So that's CO2+ and Cn minus. So that gives me CO, oops, not capital O, lowercase o. CO, what? How many CNs do I need? 2. Is this balanced? Yes, we got lucky. Woohoo! That one was already balanced for us. Okay, so sometimes you get lucky and you don't have to balance it. Previous example, we didn't. We had to balance it. Questions on this before we end for today? All right, that's where we'll stop. On Wednesday, because remember we're not here Monday, Wednesday we will be